minutes. All right, so again, a reminder of what this problem said. It said you have a piece of paper. So is it 8.5 by 11? I don't know. We just know that the dimensions are A and B. And what we're going to do is we're going to make a fold somewhere. But what has to happen is when we make our fold of this paper, we need to make sure that this point ends up, well, somewhere over here. This point P ends up over here. And what we're trying to do is we're trying to minimize the length of the crease. So I'll make the crease pink here, and I'll call this L. And I'll take these two sides, and when I fold up, of course, they still need to make a right angle. Right? So that has to be a right angle because this was a right angle. Okay. And so what they suggest doing is let's call this length X and let's call this length Y. Okay? And the idea is we want to minimize L, right? Well, to minimize L, it is easier to just minimize L squared. We've used that trick with our distance formula problems, right? So what does L squared equal from the picture? Sure, X squared plus Y squared. But one of the issues is that I have two variables, and so I'd really like to just have one variable. Right? So here I go. I guess I look at the fact that X is part of a right triangle. Yeah? Do you see it? I mean, this piece down here that's left over, do we know what that length is? It's A minus X, sure. Once I know that, okay, then I can say that I know what this piece is next. This piece would be the square root of X squared minus A minus X quantity squared. Does that make sense to you guys? I used another Pythagorean theorem. And I'm going to use one more Pythagorean theorem. I mentioned this one last time also. So I'm going to draw maybe an orange right triangle right here. Okay. And that orange right triangle right there, well, let's see. I know that this length is A, right? Oh, so what the book did, and this is not what I did. This is what the book did, which I thought was clever, was they said, let's call this length right here Z. Z is that length. So then what you notice is that you can actually simplify Z. Because if I expand this, when I square a binomial, I get a trinomial. I get A squared minus 2AX plus X squared. Right? So I get Z is just equal to the square root of what? Well, the X squareds drop out. You see that? So it becomes positive 2AX minus A squared. That's a nice way to write Z. Okay. So this point stuff right here, I guess, is what I want to do next. I'll draw this nice and pink also. See that pink segment right there? How long is that? Well, the pink plus Z has to add up to what? That's Y. Because that's the part that got folded and became the Y up here. And I think that's the piece that I may not have captured with my representation. I don't know. You need this information. So if I look at what I have now, this pink section right here, okay, we can express it in two different ways. For one thing, it would be y minus z, right? So it's y minus the square root of 2ax minus a squared. Okay. So, from this, you can now solve in the third. I basically need the orange triangle now. The orange triangle tells me if I take this mess and square it, so y minus the square root of 2ax minus a squared squared plus a squared, what does that have to equal? Has to equal y squared, right? That's the third triangle up there. Some people checked out. We okay? Keep going, Paul. All right. So when I simplify here, let's see. This becomes y squared minus 2y times the square root plus, when I square this thing, the square root goes away. So it would be 2ax minus a squared. So all that is right here. I just squared this mess. Plus a squared is equal to y squared. Lots of nice stuff drops out. Do you see it? The y squareds drop out and the a squareds drop out. And so I'm left with, let's see, negative 2y square root of 2ax minus a squared. Since everything dropped out, I will move this piece to the other side and just say this equals negative 2ax. And now the game is, let's get y by itself. So what the heck does y equal? Well, the negative 2's go away, and I just get x over the square root of 2ax minus a squared. Is it ax? Yeah, it would be. Ax, thank you. The negative 2's went away. Ax over the square root of 2ax minus a squared. All right, that's a lot of algebra we just did. And what are we trying to minimize? L squared, which is x squared plus this thing squared, because here's y. So now, here I am, I'm going to, I'll write it in black, minimize. Instead of L squared, let's call it f of x. So it's x squared plus y squared is this big ugly fraction squared. So it's ax over the square root of 2ax minus a squared. So if I simplify that, I get f of x is equal to, well, x squared plus, you can write this as a squared x squared over the square root of 2ax minus a squared. Okay. Are we ready now? We did it. We got what we're trying to minimize, and we just wrote it as a function of x. So what do? Take the derivative and then set it equal to? Yeah, I tried that. Let me show you what happens. Here's the derivative I'm taking. I did this one fine, 2x. And then I had this mess. And then I was a little bit sad. I said, you know, I bet there's a better way than trying to handle all this. And I had in the back of my mind, what if I just combine these fractions? And I'm going to tell you it works out much nicer. You see, you can write x squared as a fraction. How would you write it? Well, you could write it as x squared over 1, for instance, right? But if you want to add these fractions, you need a common denominator. So let me get that common denominator. Oh, by the way, I made a mistake. Does anyone see it? When I squared the mess, what's really nice is that not only does it become positive, but this square root should have gone away, right?
Yeah, I did that.
So my denominator is a little bit nicer now. I'm going to multiply the top and bottom of the first fraction by 2ax minus a squared. Here we go. F of x is equal to x squared times 2ax minus a squared. And then I'll have plus a squared x squared, right? And now both of these fractions are over 2ax minus a squared. And do you notice anything? Do you see more canceling? This x squared times this negative a squared, but here's plus a squared x squared. So we really made this thing a lot nicer. We have f of x, the thing I want to take the derivative of, is now just equal to 2ax cubed over 2ax minus a squared. And if you can write it as a simple fraction, one rational function, it works out nicer. All right, here I go. Take the derivative. F prime of x equals. What do? Hody high. That would be 2ax minus a squared times, I think it would be 6ax squared, right? Minus, Heidi ho, so minus 2ax cubed times what? What's the derivative of the denominator? Remember, the a's are all constants, right? So what's the derivative of the denominator? Just 2a, right? That's the only, everything else is a constant, so just 2a. All over, ho would be, well, 2ax minus a squared squared. Okay. So then you're going to take this derivative and set it equal to what? 0. And how do you make a big ugly fraction equal 0? You make which part equal to 0? The top, the numerator. So let me finish the problem over here in pink. Why not? So let's set the numerator equal to 0. So I get, if I work this out, okay, I'll just say 0 equals, and now, you guys, this is going to be messy, so let's, before we start multiplying, let's look for common factors. What do you see that's common to both sides of this subtraction sign? 2ax to what power? Squared. I agree. And then let's put everything else here in this bracket. So let's see what would be left. Well, okay, if I take out a 2ax, I have this parentheses, 2ax minus a squared times, it would just be 3, right? And if I take out a 2ax here, I would have minus x squared times 2a. Okay. So I need to work on that stuff in green in the bracket there. That stuff in green would be 6ax minus 3a squared minus 2ax squared. Yeah?
It'd be X.
Yeah,
Right, not the X plus.
yeah, I'm missing something. Where?
It'd be.
Oh, it'd be 2ax.
Yeah.
Right, this is not x squared. Otherwise, that'll be, right. Yeah? So that's just 2ax? Oh, that works out nicer, because now what do you get? You get 4ax minus 3a squared. So either this equals 0, or I suppose you could have 2ax squared is 0. So if you do this, you get x is 0. That's kind of interesting. That's a critical value. And over here, if I solve for x, I get, let's see, 3a squared over 4a, which is 3/4 a. X equals 3/4 a. So there's my critical values, 0 and 3/4 a. All right? Looking back at the picture, let's see what it would mean. All right, so if x is 0, you would just start at this corner and fold, and you'd be basically folding the square in half, right? So then you would get the diagonal of the square would be a radical 2. It turns out that's the maximum length you can get, okay? And it turns out that you can show that this is the minimum length you can get. Now the minimum length, I guess, how would you show it? You either do a second derivative test or a first derivative test. You could show that this derivative decreases before and increases after. Okay, I'm not going to do that, but I think it's a cool answer. 3/4. So you know, I don't know if this is a 9 by 13 or something. You would want to do 3/4 of 9, or what 3/4 of whatever a is what you want if you want to minimize the length. I think that's kind of cool.